root locus is locus of roots of characteristic equation as k varied from 0 to infinity. It is also said to be a graphical approach. Root locus is a graphical approach to find stability. And the requirement to draw the root locus is the characteristic equation, and it is given by this. And we can write this equation as g of s h of s equal to -1, and this can be split into two conditions. One is magnitude condition. The mod of g of s into h of s is equal to 1 is known as magnitude condition, and angle g of s into h of s equal to 180 into 2q plus 1. This is known as angle condition. These two conditions are developed by Evans, the name of the scientist. Root locus must satisfy these two conditions known as magnitude and angle condition. For every point to lie on root locus, it must satisfy the angle condition first. Then if it satisfies angle condition, then magnitude condition is used to find out the value of k at any point on root locus. So let us see the rules to construct the root locus. Rule 1 says that the root locus is on or symmetrical to real axis. The meaning of this rule is the roots given of any system may lie on real axis, or if it is a complex poles, they are symmetrical to real axis. If they are complex zeros, they are symmetrical to real axis. So the given root locus is on real axis or symmetrical to real axis. Rule 2, the number of root locus branches equal to p, that is given by number of poles, if p is greater than z, and is equal to z if z is greater than p. So in this root locus, it exists always poles will be greater than zeros, or at the most they may be equal to zeros. Now rule 3 says the for any point to lie on root locus, the number of poles and zeros together to the right of the section must be odd in number. For example, g of s into h of s is equal to k into s plus 1 into s plus 5 divided by s into s plus 3 into s plus 10. If you look at this problem, the root locus existence on real axis for any point to lie on root locus on real axis, we need to represent the poles and zeros on the S-plane. So the poles are given here at S is equal to 0, minus 3 and minus 10, and the zeros are at minus 1 and minus 5. If you locate them in the S-plane, all are real only, poles and zeros. So the pole is at origin and at minus 3 and at minus 10, and the zeros are at minus 1 and minus 5. So all the poles and zeros are existing in this problem on real axis only. Now the root locus existence on real axis must be seen. Suppose if I put a point here, towards the right the number of poles and zeros must be odd in number. So root locus exists between this pole and 0, and root locus doesn't exist between these two because towards right the number is even. Again, when you come here, the root locus existence will be there here because to the right of this particular point or section the number is odd. Similarly, root locus doesn't exist here and it exists beyond minus 10. It is important to note that the root locus starts from a pole, and ends at 0. Root locus starts from a pole and ends at 0. So the existence of root locus on real axis is known from rule 3. So this is the way we should represent the existence of root locus on real axis, by seeing the number of roots, that means poles and zeros, to the right of that section must be odd in number. Rule 4 gives an idea of asymptotes. Asymptotes are tangents drawn to the root locus at infinity. So in other way round, they are root locus branches approaching infinity. As I mentioned that the root locus starts from a pole when k equal to 0 and it ends at a 0 at k equal to infinity. Now, in a particular problem, that if the number of poles are greater than number of zeros, then the asymptotes, number of asymptotes are given by P minus Z. If P and Z are equal, then no question of existence of asymptotes. So, this is the formula to find out the number of asymptotes in the given problem. If number of poles are 3 and number of zeros are 2, then number of asymptotes are 1, and that is the tangent drawn to the root locus at infinity. With the help of this asymptote, we will draw the root locus. Now, in which angle the asymptotes will move, that is given by angle of asymptotes. This is given by theta 180 into 2q plus 1 by P minus Z, the formula that is used to calculate the angle of asymptotes, where q is equal to 0, 1, 2 depends on number of root locus branches. Number of root locus branches. So, these asymptotes are also symmetrical to real axis. Asymptotes are symmetrical to real axis. If P is equal to Z, then no asymptotes. This is to be noted. So, rule 4 is about finding the number of asymptotes and also the angles at which the asymptotes are to be drawn. The number of asymptotes will depend on the number of root locus branches. Rule 5 is to find out the centroid. Centroid is nothing but meeting point or junction of asymptotes on real axis. Meeting point or junction of asymptotes on real axis. This is represented by sigma, and it is given by sigma real part of poles minus sigma real part of zeros divided by P minus Z. This is the formula used for finding the centroid. And this centroid may or may not be the part of the root locus. The meaning of this is centroid may exist on root locus or it may not exist on root locus, but definitely it will be on surely real axis. Let us consider one problem. G of s into h of s is given by k by s into s plus 5 into s plus 10. Now, the question here is find out number of asymptotes, then angles of asymptotes, then centroid. Now, in this case, to find out the number of asymptotes, the number of poles here are at s is equal to 0, at s is equal to minus 5 and at s is equal to minus 10. And the zeros does not exist in this problem. Poles are only 3. So, to calculate the number of asymptotes, is equal to P minus Z. So, it is 3 in this case. All these 3 asymptotes are the tangents drawn to the root locus at infinity. So, we must calculate the angles of asymptotes. They are given by angles of asymptotes is given by 180 into 2q plus 1 by P minus Z. Now, Q should be taken 3 values because the number of root locus branches are 3. So, angles of asymptotes are calculated for different values of Q, and Q here it has 3 values. So, for Q equal to 0, the angle of first asymptote theta 1, if you substitute Q equal to 0, you will get 60 degrees. For Q equal to 1, theta 2 will be 180 degrees. For Q equal to 2, theta 3 will be 300 degrees. These are the angles of asymptotes for this particular example. Problem continuation, third bit, to find out the centroid of the given system is given by sigma real part of poles minus sigma real part of zeros by P minus Z. So, real part of poles, there are 3 poles located at 0, minus 5 and minus 10, and there is no real part of zeros. So, it is simply 0 by P minus Z, it is equal to 3 minus 0. So, this will be minus 5. So, the centroid is located at minus 5. So, the pole is at origin, pole is at minus 5 and pole is at minus 10. No zeros exist in this problem, all the 3 are poles. Now, the centroid is at minus 5. So, this is the point, the centroid exists. And if you see that the meaning of centroid, it is the meeting point of all the 3 asymptotes. So, as it is given that 3 asymptotes having an angle of 60 degrees, 180 degrees and 300 degrees. We need to draw the straight lines from minus 5, this is the meeting point of the asymptotes, drawing a line making an angle of 60 degrees in counterclockwise direction, and the another one is at minus 180 degrees along this negative real axis, and another asymptote is drawn by making an angle of 300 degrees from this centroid. So, this angle is 300 degrees. So, this is the asymptote 1, this is asymptote 2 and this is asymptote 3. Problem 2 on rule 5, g of s into h of s is equal to k by k into s plus 10 by s square into s plus 1. For this problem, find angles of asymptotes and centroid. Now, the poles are at s is equal to origin and origin. There are 2 poles and one pole is at minus 1. And the zeros at s is equal to minus 10. So, the number of asymptotes are equal to p minus z, it is 3 minus 1 equal to 2. And angles of asymptotes are theta equal to 180 into 2q plus 1 by p minus z. Only two angles we need to calculate, theta 1 for q equal to 0, and this angle will be 90 degrees. This is for q equal to 0, and theta 2 is to be calculated. It will be 270 for q equal to 1, because the number of asymptotes here are only 2, p minus z. So two angles of asymptotes are to be calculated. Now to calculate centroid, represented by this symbol, and it is sigma real part of poles minus sigma real part of zeros by p minus z. So it will be minus 1 plus 10 by p minus z is 2, and this is 4.5. So if you try to locate the centroid on real axis, it is at sigma 4.5. Centroid is here, whereas the poles, two poles are at origin and one pole is at minus 1 and the 0 is at minus 10. So you can see that centroid need not be on root locus. So if you see the existence of root locus on real axis, root locus does not exist here, because towards the right the number is even. It exists here between this pole and 0. It exists between this pole and 0. So it moves from this pole to this 0, one root locus branch. Now these two poles located at origin does not have any finite zeros, so they must be terminated to infinity. So this is the two asymptotes. One is drawn at an angle of 90 and the other one is drawn at an angle of 270. Two asymptotes exist. So one of the poles will move towards that asymptote to find the 0 located at infinity, and the another pole located at origin will move towards another asymptote which is making an angle of 270 degrees. So the centroid of this particular system is not part of the root locus, but it exists on real axis at 4.5. Rule 6 is breakaway point and break-in point. So breakaway point exists between two adjacent poles, whereas break-in point exists between two adjacent zeros. Of course, it depends on the location of the poles and zeros on S-plane. So breakaway point, let us consider simple example that there are two poles one is at 0 origin and the other one is at -2. Now the rule 1, 2, 3, 4 which are says here the existence of root locus on real axis is between these two roots, and the value of k here is 0, the value of k here is 0. Now as you increase the value of k from 0, this root will move towards left and this root will move towards right, and both the poles will meet at some point on real axis. That point is known as breakaway point. Breakaway point means the value of k is maximum at breakaway point on real axis. Now further increase of k makes one pole will move towards up, the other pole makes towards down. So this is to know that how the root starts moving after breakaway point. We need to take the help of asymptotes. So in this particular example, two asymptotes will exist. One asymptote makes an angle of 90 and the other asymptote makes an angle of 270. So certainly the two poles will move, one towards up and other towards down, but however the value of k at this breakaway point is maximum on real axis. Of course, further increase of k up to infinity, one root will move towards up, and for k equal to infinity further it goes down. So breakaway point exists between two adjacent poles. Coming to the break-in point, it exists between two zeros. Break-in point exists between two adjacent zeros. To understand better the rule 6, consider the problem g of s into h of s equal to k by s into s plus 1 into s plus 3 into s plus 4. Now rule 6 is to determine the breakaway point. So find breakaway point location. Just to see this, the poles are located s equal to 0, -1, -3 and -4. One pole is located at origin, the another one is at -1, at -3 and -4. All the poles are on real axis. Now between which adjacent poles the breakaway point exists? In this case you can see here or here or here. To understand this, as you know, the value of k here is 0. As k increases, now to draw the root locus, which poles will move towards which direction? So as you know that root locus will exist between these two adjacent poles, because when I put a point or line like this towards right, the number of poles and zeros must be odd in number. So root locus exists here. Root locus does not exist here, and it exists here again because the number towards right is odd. Now I can put arrows because this pole is not permitted to move left. So I can draw arrow like this. For this pole I can draw arrow like this. Similarly, this pole will move towards left only. this pole will move towards right only. So certainly this is some location. Breakaway point exists between 0 and -1, and another breakaway point exists between -3 and -4. So in this example, there exist two breakaway points. Two breakaway points exist in this particular example, and further increase of k will certainly make the poles move in different angles in S-plane. That is to be calculated using the formula angles of asymptotes and centroid. However, this rule 6 says only breakaway point. So breakaway point exists between 0 and -1, and it also exists between -3 and -4. G of s into h of s is given by k into s plus 1 into s plus 3 by s square. So location of break-in point. The poles at origin only, but the zeros are at -1 and -3. So if you see these two poles exist on origin, whereas one 0 is at -1, the another 0 is at -3. So the break-in point exists between two adjacent zeros. That means, as you know, that root locus will exist here only between these two adjacent zeros. So somewhere here the break-in point exists. Break-in point exists. So to know the breakaway point or break-in point, the value of k must be positive for that particular point, whether it is breakaway or break-in, but the value of k must be positive for those points. Then only they are valid breakaway or break-in points. G of s into h of s is equal to k by s into s plus 2 into s plus 4. Now find breakaway point for this given system. Now we need to get the characteristic equation. So 1 plus g of s into h of s equal to 0. That means 1 plus k by s into s plus 2 into s plus 4 equal to 0. This is equal to s cube plus 6s square plus 8s plus k equal to 0, and from this the k is given by minus of s cube plus 6s square plus 8s. Now the breakaway point is to be calculated because the value of k will be maximum on real axis. So I can use this formula dk by ds, differentiate the k with respect to s and equate it to 0. This is the condition for breakaway point to be calculated. So dk by ds is equal to 3s square. You are differentiating this plus 12s plus 8. Now this is equal to 0. Now if you solve this second order characteristic equation, solving for roots, you get s1 and s2 as minus 0.814 one value and minus 3.15 another value. Now I am in dilemma to consider which one is the valid breakaway point. There are two ways to find out the valid breakaway point. For that, let us put the poles on S-plane. One is at origin, the other one is at -2, the other one is at -4. So there are only 3 poles that exist in this system. So which breakaway point is the valid breakaway point? To know that, -0.814, it exists between 0 and -2, somewhere here. 0.814. The another one exists here, -3.15. But only one is the breakaway point here, because as you know very well that the root locus exists between these two adjacent poles, but it does not exist between these two, because the basic rule says towards right, when you put a point, the number must be odd. But this is even number, so root locus does not exist between -2 and -4. Whereas root locus exists after -4 towards infinity. So the valid breakaway point is this. -0.814 is the valid breakaway point. Valid breakaway point is -0.814 and not -3.15. This is one way of looking at the breakaway point easily when you locate poles in the S-plane. And another way is substitute these breakaway points in K. You can substitute these roots S1 and S2 in K is equal to minus S cube plus 6s square plus 8s, and see that value of K must be positive. So when you substitute minus 0.814 or minus 3.15, the K value must be positive. So definitely, if it is an invalid breakaway point, the K value will not be positive. So this is another way of calculating the valid breakaway point. The value of K must be positive when you substitute that root in equation K. The problem on rule 6. G of s into h of s is given by k into s plus 4 by s into s plus 2. Now find breakaway and break-in points. The poles are at origin and -2, and the zeros at s is equal to -4. When you try to locate them in the S-plane, pole is located at 0 and another pole is located at -2 and the 0 is located at -4. Now, to determine the breakaway and break-in points, we must get the characteristic equation equal to 0. So s square plus 2s plus k into s plus 4 equal to 0, and k is equal to minus of s square plus 2s by s plus 4. So once you get the k from the characteristic equation, we need to differentiate this d k by ds and equate it to 0. So to differentiate this s plus 4 as it is, and s square plus 2s as 2s plus 2 differentiation, minus s square plus 2s as it is into 1 by s plus 4 whole square. So you are differentiating k with respect to s and equate it to 0 and solve for s value to get breakaway and break-in points. So you need to differentiate k with respect to s and equate it to 0 and solve for the roots. You will get s square plus 8s plus 8 equal to 0. This is the equation after differentiating and equate it to 0. And if you solve for the roots s1 and s2, you get minus 1.17 and another root is minus 6.82. The location of poles and zeros in the S-plane are given. There are 2 poles exist and 1 zero. So as you know that root locus definition is root locus starts from a pole and ends at 0. But here there are 2 poles but only 1 finite 0. That means I can say that the poles are at origin and minus 2. Then zeros, one is there at minus 4, no problem. But the another 0, I can assume that it is at minus infinity. That means one pole will terminate at finite 0 and the another pole will terminate at minus infinity. Now the problem here is where is the breakaway point exist and where is the break-in point exist. According to the definition, breakaway point exists between 2 adjacent poles. So the root you obtained minus 1.17 from differentiating k with respect to s, breakaway point exists between 0 and minus 2 as minus 1.17 and break-in point is at minus 6.82. That means these 2 roots move towards each other, they break at this particular breakaway point and then one pole move in a circular fashion, reach the break-in point and another pole also will move in a circular fashion to reach the break-in point. Now at this break-in point both the poles meet and one will move towards minus 4 and another pole move towards minus infinity. So you need to assume that the 0 at minus 4 is called finite 0 and there is another 0 at minus infinity. So the break-in point exists between finite 0 and infinite 0 and breakaway point exists between 2 adjacent poles. Rule 7. This is to say about the intersection point with imaginary axis. Finding the intersecting point on imaginary axis. To find out the intersecting point on imaginary axis, the procedure is form the characteristic equation, then using this characteristic equation construct the RH table using RH stability criteria, then find the value of k gain for marginal stability and then auxiliary equation is to be obtained, and the roots of this auxiliary equation are intersecting points on j omega axis. And how to know the valid intersecting points? Valid intersecting point is the point or the root for this, the k marginal must be positive value. So this is the way you should find out the intersecting point on j omega axis. Problem on rule 7. G of s into h of s is equal to k by s into s plus 2 into s plus 4. Find out intersecting point on j omega axis. So according to the rule, once the function is given, we should get the characteristic equation 1 plus g of s into h of s is equal to 0. The characteristic equation of the given system is to be obtained first. Then simplify this equation. You will get s cube plus 6s square plus 8s plus k equal to 0. This is known as characteristic equation, and using this equation now we need to form the RH table. RH table. Take the highest power of s as a first row, second highest power of s second row, and the coefficients of this characteristic equation are to be given in the first two rows. Coefficient of s cube is 1, and alternate terms coefficient of s is 8, and for s power 2 row the coefficient is 6 and alternate term is k. First two rows of RH table are from the coefficients of characteristic equation. Now you need to obtain s power 1 row by multiplying this cross multiplication, 48 minus k by 6, and you can consider this as 0, and s power 0 is obtained again by cross multiplication and dividing by this, you will get k. According to the stability, the first column of Routh array, there should not be any sign change for the system to be stable. So here, how to find the value of k for marginal stability? That means k should be greater than 0, and 48 minus k by 6 also must be greater than 0. So that means the marginal value of k, will be 48. That means system is stable between 0 and k 48. So k is 48 is the maximum value for stability. Beyond 48 the system becomes unstable. So now auxiliary equation is to be obtained for marginal value of k. So auxiliary equation is taken from s power 2 row, that is 6s square plus k equal to 0. I should put the value of k here as 48. And then we should solve for s. So 6s square is equal to 48. S square is 48 by 6, means this is 8. So s is equal to plus or minus root 8. So you get now two roots from the auxiliary equation and they are the intersecting points. If you locate these two roots in the S plane, originally the poles are given at s is equal to 0, s is equal to minus 2 and s is equal to minus 4. So these two roots will have a breakaway point somewhere here, and then one root will move towards this way and one root will move towards this way. So our interest in this problem is to know the intersecting point on j omega axis. So plus root 8 and minus root 8. So this is the way the value of k for marginal stability is 48, means the pole reaches the intersecting point at k is equal to 48 and k is equal to 48. Beyond 48, the system becomes unstable. Rule 8 is to find out the angle of departure for complex pole and angle of arrival for complex 0. Angle of departure is represented by theta d and angle of arrival is represented by theta a. So theta d is calculated using the formula 180 plus the angle of g of s into h of s, and this angle is for positive complex pole, and theta a is calculated using the formula 180 minus angle of g of s into h of s for complex positive 0. This is essential to calculate if any complex pole or complex 0 exists in the problem. Problem on rule 8. G of s into h of s is equal to k into s plus 2 into s plus 4 by s square plus 2s plus 2. Now find out theta d, angle of departure for complex pole. So the poles are at minus 1 plus j1 and minus 1 minus j1. The zeros are at minus 2 and minus 4. If you locate them in the S plane, the complex poles are at minus 1 plus j1, minus 1 minus j1. So there are two complex poles exist here, and the two zeros are at minus 2 and minus 4. Now there is no problem that the root locus exists between these two adjacent zeros, because towards the right the number of poles and zeros must be odd in number. So 1, 2, 3, it is an odd number. So root locus exists between these two adjacent zeros. Now what about these complex poles, they must move as you increase the value of k from 0. So k is 0 here, k is 0 here. Now when you increase the value of k, this pole must start moving and reach the 0. That is what the root locus. So to calculate this angle of departure, we need to calculate theta d for positive complex pole is given by 180 plus angle g of s into h of s for positive complex pole, that means minus 1 plus j1. Now you need to calculate the angle g of s into h of s for positive complex pole, that is s is equal to minus 1 plus j1 in the given function. The given function is k into s plus 2 into s plus 4 divided by s plus 1 plus j1 s plus 1 minus j1. I have written the denominator into two poles. Now substitute s is equal to minus 1 plus j1 in the given function. So this one, k does not have any angle contribution. Now substitute minus 1 plus j1 plus 2 and s is equal to here minus 1 plus j1 plus 4 divided by s is equal to minus 1 plus j1 plus 1 plus j1 and minus 1 plus j1 plus 1 minus j1, because you are trying to calculate angle of departure for positive complex pole. So the k as it is, no change. Now this will be 1 plus j1 and this will be 3 plus j1 divided by minus 1 plus 1 gets cancelled, j2 only remains, and here minus 1 and plus 1 plus j1 and minus j1 gets cancelled, so nothing will remain. In the denominator it is only j2. Now the angle contribution of each and pole and each 0 has to be represented. Here contribution of k is 0, contribution of 1 plus j1 is 45 degrees and angle contribution of 3 plus j1 is 18.63 and angle contribution of j2 is 90 degrees. Now if you calculate the resultant angle, here you get minus 26.58 degrees. This is the angle contribution of g of s into h of s. To calculate angle of departure now, theta d is 180 plus angle contribution of g of s into h of s. This is equal to minus 26.58 degrees. So this comes to 153.43 degrees. So angle of departure is the starting of the pole as you increase the value of k from 0 to infinity. So this is the complex pole you have at minus 1 plus j1. So you need to draw a line by making an angle in counterclockwise direction of 153 degrees. Then the root locus will start from this complex pole in this angle and reach the breaking point. Similarly, the other complex pole having minus 1 minus j1, also you angle of departure for this complex pole will be minus 153 degrees. So you need to have minus 153 in clockwise direction and this pole also will move in this fashion and reach the break-in point. So this is the root locus for this particular example, but here our interest is only to calculate angle of departure, that is equal to 153 degrees.